Hello everyone, thanks for watching this video. Today I'm going to talk about our work, Tensor Network for Supervised Learning at Finite Temperature. This is a joint work with my collaborator Shu Qianye, who conducted the experiment, and my supervisor Xi Zhu from ELS, CUHK Shenzhen. The large variation of dataset is a huge barrier for supervised learning tasks. While in physics, the thermal fluctuation may flatten a large variation. In this paper, we import the thermal perturbation into the matrix product framework by placing all images in an environment with constant temperature. Such placement is realized by introducing an extra temperature layer. This presentation is organized as follows. First, we briefly introduce the basis of this work, matrix product state framework for supervised learning, as well as the METTS algorithm. Combining these two concepts, we construct the tensor network structure at finite temperature. Following is the corresponding contraction and optimization algorithm. Then, results and some interesting discovery are then stated. Finally, I will illustrate the physical interpretation and outlook. For illustration, we focus on the image classification task, even though this adjustment can be used for other tasks. As shown in the slides, the two-dimensional image is mapped into a one-dimensional chain through a zigzag order. Following this order, the entire feature map is formed by connect product of all local feature maps. The local feature map can be non-linear kernel, like the trigonometric function. It can also be a one-hot-like coding. Actually, the local feature map is not the corner part of this work. Then, the matrix product state, which is the contracted sequence of low-order tensors, is used to approximate the weight tensor. The connecting edge is called the bound dimension. As for classification tasks, all low-order tensors are connected to the local feature map, except the label tensor, which represents the final prediction. Through connecting and contraction, the entire tensor network gives a final decision. This framework is in analog to calculate the average value of an observable when the feature map only consists of real numbers. Differences between physical and machine learning representation mainly comes from the conjugate of feature map, or in physics, the wave function. Indices connected to the upper and the lower layer are generally the same, or sometimes conjugated. In other words, if we truncated one of these two indices, the physical representations becomes the machine learning representations by treating the observable as a modified weight tensor. Minimal entangled state is a very successful algorithm that can simulate finite temperature quantum systems. The main idea of this algorithm is to sample the thermal fluctuations by randomly select quantum states rather than classical ones. It can be noticed that the adjustment is the insertion of an exponential term compared with the original expression. Then the expectation value is estimated by sampling the state with its probability and averaging the expectation value computed at each step. I will not go further into the technical detail in the aspect of physics, since this work mainly focuses on machine learning, but you will see the interpretation of it later in this talk. Inspired by the METTS algorithm, we propose the MPS framework at finite temperature. In the first step, we transfer the tensor network structure in machine learning representation into physical representation. The feature maps are transformed into two input functions as shown in the slide. Then we can see that main difference is the number of edges, or the rank of tensor. For the weight tensor, we want to introduce an extra edge. For the individual tensor of machine learning representation, if we fix its edge connecting to its adjacent, the remaining part is a vector. While for the individual tensor of physical representation, if we still fix its edge connecting to its adjacent, The remaining part is a matrix. Now, the diagonal element of this matrix is set as a vector in machine learning representation. After this, the recovery step, the temperature layer is then inserted. This temperature layer is the exponential of individual tensors with a coefficient beta. Notice that the weight tensor is diagonal, so the exponential does not take much computational cost. Then, we connected the weight tensor, the temperature layer, and the wave functions together. Notice this framework is similar to the tensor network structure in METTS algorithm. The first step, recovery, is conducted to make sure the number of edges are enough. To reduce the complexity, we truncate the upper part. Notice that the weight tensor is a diagonal matrix, so its edge connecting to its adjacent are fixed. So the mapping to it to a vector does not lose information. There still exists a special tensor which is called the label tensor, which does not connect it to the feature map. For this tensor, we do not increase its rank, but the temperature modified tensor is still added. In this way, the architecture is well set up. For more detailed description, please refer to our paper. For the classification task, the construction of entire tensor network gives a L by 1 vector, whose largest element corresponds to the output class. For the optimization algorithm, the loss function is defined as multi-class closed entropy function. The most time costing process is the contraction of the entire tensor networks. Here we adopt a parallel contraction algorithm, which possesses an advantage that each step is parallelized as matrix multiplication, without requiring the calculation results from the neighboring calculation. This optimization process contains 3 steps. For the first step, the temperature tensor is contracted with its corresponding weight tensor and the local feature map, giving a new tensor depicted as green squares. After this step, we contract the generalized tensors in pairs. This step is conducted independently for each pair of them in parallel. This step is repeated until the tensor chain is fully contracted. There are 2 optimization methods, which are automatic gradient and the DMRG-like sweeping algorithm. It is observed that training with automatic gradient is nearly independent of the use bound dimension, while the bound dimension matters when using the DMRG-like sweeping algorithm. One possible reason is that the DMRG-like sweeping algorithm changes the bound dimension during training. We want to focus on the temperature effect, so the automatic gradient descent method is utilized. To illustrate the effect of the temperature layer, we use a setup as this paper. The dataset is feature maze, which is a large variation dataset. The image size remains unchanged, 28 by 28. The optimization is at demo. The learning rate is 10 to the power of -4. The batch size is 50. The loss function is set as the multi-class closed entropy. The feature map is 1 minus XX. This feature indicates the accuracy of test set. Notice that here, without thermal perturbation represents the tensor network framework, without temperature layer, while with thermal perturbation represents the best result calculated by our method. We can see that, in general, the endorsement of temperature layer gives a better performance in test accuracy. For the best case, at the bound dimensional 22, accuracy increment is around 1%. Originally, the test accuracy first increased with the increased bound dimension, while it goes through a decrease after a critical number. Such decrement may come from overfitting. Unfortunately, the actual temperature layer does not change such tendency. Until now, I shared the main part of our work. I want to share you with some interesting discovery, although it is not the core of this work. As can be seen, compared with original tensor network framework, our work includes an extra hyperparameter, beta. We tried to optimize it through a simulated annealing algorithm with no change of other parameters, like learning rate, batch size, etc. The temperature-like parameter beta finally converged to a constant despite of different setting of bound dimension. We believe that the least temperature layer is only a function of dataset, or in other words, the intrinsic property of dataset. Obtaining such property might be useful in training other machine learning-based tensor network frameworks. Until now, I have illustrated the programming part. The following are theoretical interpretations. First is the physical interpretation, which is mainly about METTS algorithm. According to the elementary principle of quantum static mechanism, the average of an observable at a finite temperature is calculated by summation of all states observed with different probability. Here, our method of temperature endorsement is in analog to METTS algorithm. Notice there is another interpretation of MPS classifier. The weight tensor is a combination of all standard image or feature map vector in a given class. The contraction of tensor network states gives the inner product. In other words, the weight tensor contains the typical set of states which are used in METTS algorithm. We take exponential of it. We calculate the corresponding value at finite temperature. The normalized parameter Z is omitted since the final result is only determined by the largest value of output vector. Or in other words, we place all these images in an environment with certain temperature. This temperature is the hyperparameter in this work. For intuition interpretation, let us just imagine a perfect straight line or picture. Both human and computer can easily distinguish it. However, if a line is slightly bent, human can still treat it as a straight line, but for computer, by accurate correlation, the line is treated as a curve rather than a line. At finite temperature, the bent line is treated as the combination of the curve. The small perturbation may be ignored. Physically, the curve state is not excited, or not excited without temperature. While then, the line state is the ground state, which always exists. One can say that the temperature-like parameter is in analog to a threshold. Slightly bent lines are treated as line, while the highly bent lines are treated as curve. When it refers to the image classification tasks, we can say that the feature map is separated by thermal fluctuation. Notice that there is an exponential term separating the standard features. So here we can say, with proper setting of temperature-dependent value of beta, similar features can possess a reasonable separation, which gives a better performance. Mathematically, for a small value of beta, this temperature layer approach identity matrix corresponding to the original MPS structure. For significantly large value of beta, due to the exponential decay, the variation between features approach zero, leading to an entire black image. A proper value of beta will emphasize the main feature and benefit the training process. In conclusion, we introduce a thermal perturbation into the tensor network structure by insertion of a temperature layer. This thermal perturbation gives increment on test accuracy, without greatly change of original tensor network framework. For feature development, notice that the temperature can be endorsed in other feasible tensor network frameworks, like the PEPS, MERA, the comp tensor network, and etc. From my intuition, the multi-scale entangled renormalization on SAS is expected to be the best platform, especially for the computer vision field, since its structure is in analog to the convolutional neural network framework. We believe these tensor network frameworks are also suitable platform to endorse finite temperature. Thanks for listening.
Thank you, Haoxiang, for the presentation. So now there are a couple of questions in the chat. Can you see them? And maybe if you can read them and answer to them. Thank you.
All right. So the first question, can you choose the range of bound dimensions? In practice, is it possible to be learned automatically? I have to say the bound dimension is one of the hyperparameter in something like MPS classifier and some other tensor network structure for machine learning. So actually, I can change the range of bound dimension. Yes, but for large bound dimension, it is possible that the tensor network structure encounter overfitting and performs very badly. I have to say, much better than some lower dimension. So a proper bound dimension is good for other things, for tensor network structure. So there exists another kind of optimization algorithm, which is the DMRG, like sweeping algorithm. In this step, the bound dimensional is optimized along the optimization process, I have to say. So, but its initial value is very important. So I have to say it is possible to be learned automatically. Yes. The second question is how the temperature value is optimized for a machine learning task. Actually, I can say the temperature value is a hyperparameter in our work for my test. You can try to optimize it as a hyperparameter, just as I stated. But also, you can try to use other optimization algorithm as stated, like annual simulated annually. So actually, it is optimized. Okay, so the third question, is there any relation to data augmentation? Yes, there may be some relationship. For data augmentation, we treat each figure as some many figures. For example, like segment. We segment the image into several pieces, and we feed the network with many images, more than one image. Then the network may perform better. In this work, we can see that I inserted another temperature layer, I can say. So you can see that suppose the data, or in this work, the image is suitable for the tensor network, then the tensor network will learn more about it. But if the image is not suitable for this tensor network, maybe the tensor network just learn little about it. They just develop it a small amount. So there may be some relationship to data augmentation. All right, that's the answer.
There was also another question from Chaoli just before the one from Chipin that was asking what would happen if the exponent function in the model is replaced by another nonlinear operation. Can you replace the exponential with some other nonlinear function? Is it possible? It's a question that was asked in the chat before Chipin's question.
I'm sorry that my connection is bad, so that
I put the additional question at the end of the chat, if you can see it.
Okay, the question is, what would happen if the exponential function in the model is replaced by other nonlinear operations? Is there any alternative? Actually, we tried some other nonlinear operations, for example, like a ReLU function, for example, like some other activation functions. But actually, from my test, this function does not perform better. For which activation function? For some activation function, is sometimes the converged even does not appear. The optimization does not converge even for some nonlinear operations. But actually, from my intuition, some activation function like ReLU function is not physical meaning. Because it does not represent some like it. So that is the answer. Thanks.
All right. Thank you very much, Haoxiang, for the answers and your talk.